So I'm working for a company called Polytechnic, and just to do the brief marketing pitch here. So we are a 60-year-old company, having our roots in the combustion of biomasses. We are Austrian-based, and 95% of our business is export. And we export to various countries in the world. So headquartered in Austria, we have either sales reps or subsidiaries around the world. And in the next slide, I show where we have been doing businesses in the past before we had the war between Ukraine and Russia. Russia was a relevant market for us. Today it is Europe, it is New Zealand, but we have a global footprint, as you can see. With regards to our history in torrefaction and carbonization, that dates back to 2009, where we, together with other Austrian companies, worked in torrefaction, and we came up with a process to use these low-caloric syngases for the process for the roasting of the biomass. We have been involved in this pilot plant since 2009. We are in the moment, and that's what I'm going to talk about an industrial plant for torrefaction, 60,000 tons, that's currently going through the ramp-up commissioning. And we are also, there's a typo there, since 2016, we have a carbonization pilot plant in Germany with a nominal capacity of about 3,000 tons. So, Hans-Jörg, we have to talk. So, a little picture of our machinery and equipment that we have there. What I'm going to talk about now is the use of these syngases in the process of torrefaction and carbonization. And the upper graph picture is torrefaction. There we use a rotary kiln, and the lower picture is our process that we have installed in our pilot plant, the carbonization plant in Germany, where we are utilizing a batch process. Here we just brief description, differentiation, torrefaction, carbonization. When I talk to potential customers outside of our industry, I always say, hey, we're talking about light roasting and dark roasting. Light roasting for torrefaction, carbonization, the dark roasting. Main difference is the caloric value and the C-fix. And using that again, torrefaction, light roasting, different temperature of the roasting, carbonization, higher temperature, and all the things that we've seen on Hans-Jörg's presentation. The key advantages of the two processes is reduced moisture content, enhanced biomass energy density, and improved fuel properties. Light roasting torrefaction has less volatiles, has more volatiles, less caloric value in differentiation. On the right, torrefied biocarbon has about 20 to 23 megajoules per kilogram. Interesting for utilities, substituting coal for particularly heat generation, power generation, and carbonization in the ballpark of 27 to 30 megajoules per kilogram. The process, that's what we offer our customers, from feedstock preparation all the way down to densification. And the process is in principle the same for torrefaction and carbonization. big difference is torrefaction is if it runs in an energetic equilibrium, and as we've seen on Hans-Jörg's slides, in carbonization there is excess heat and or electricity that we get out there. Here's an example. If we use the same freshwood chips in our torrefaction process, it's autothermal, 350,000 tons of freshwood chips in. We get roughly a little bit less than 150,000 tons of bio coal out there. And if we do that then for the carbonization, considerably less biocarbon, but more energy, in this particular case for electricity and for cooling them. Here is a typical composition of the syngases that do get set free with the pyrolysis of the biomass. And the challenge is its low energy density and high tar content. And we have, as you've seen, we have been working on that topic since 2009 in pilot plants for torrefaction and for carbonization. And the advantage of such an indirect reactor is that it provides a controlled environment for the processing. It prevents contamination, and it uses the internal gases. In our discussion with customers, potential customers, this becomes considerably relevant for we can reduce the CO2 footprint. The big discussion for the customers is CO2 footprint, CO2 footprint, CO2 footprint. And using the syngases is a really a key ingredient of reducing that. And as we had seen on Hans-Jörg's presentation, the energy that we get out of the processing, it could be then used further. Typical applications or usages are via thermal oil, steam, heat distribution, or an RC process. Here we see the industrial implementation of this torrefaction plant that I've mentioned earlier. Our customer in Finland, this is a 60,000 ton out annual on a production out basis. So it's 8,000 tons an hour. And you can see here the footprint of where our plant or the plant is about 10,000 square meters. Here you see the reactor on the right side of the picture, and on the left just a demonstration on the dimensions. You see a small person here, the reactor, the boiler, the furnace. So we're talking big equipment, and this is all torrefaction. But as I try to state, and hopefully I get it across, these syngases are also used for carbonization. In our particular case here in the Finnish plant, the LHV is about 13 megajoules per kilogram. And we had a special, when addressing this particular case here, we looked at the combustion chamber, the optimum gas flow into the gas combustion chamber, and we optimized the combustion process. And the idea or the result was that we have a very high tar decomposition with very low emissions. We have a very good efficiency and a high level of plant availability, and the service life is also very, very good. From what we see in the market and what we have seen market in principle, in particular here with our Finnish customer, the syngas integration reduces the footprint. This is the big topic from potential customers. The indirect heating ensures an optimal process, and the future focus for us is refining the burner technology, and then, of course, talking about the syngas purification. So thank you very much for your attention. And I think we have a little bit of time left if we have any questions. Also questions maybe on the part of Hans-Jörg's presentation, if we still have. So questions on that.
Thank you very much, Howard. I think it's very impressive, this 60,000 ton plant. Also, I saw the pictures of the reactor before. That's a massive thing. My first question would be, so the torrefied biocoal, as you call it, that's used for energy utilization.
That's correct.
And just in theory, could you increase the temperature in this kind of setup, or?
I'm not sure that I fully understand the question. Let me try to answer what I think you are asking, and then you correct me.
Yeah.
So as we have seen on one of the slides here, torrefaction, carbonization, light roasting, dark roasting. But even on the light roasting, there's a certain range of caloric value that you can get out of the product. And so that very much is dependent on what the customer wants to have. And the range we can offer and we can deliver is between 20 and 23. And then we have the discussion whether it's gross caloric value, net caloric value, but that's the ballpark. And that then influences many of the other things, like and it's primarily a combination of what's the feedstock input, one thing, and the second is what's the usage of the torrefied material in terms of where is it going to be used and what type of densification the customers want to achieve.
Yeah, I think you touched a bit on what I wanted to ask, but Frederick from Soler is asking a very similar question. So I just read it out loud. If I understood well, you associate a continuous rotary kiln for torrefaction with a batch continuous process for pyrolysis. Would you have the possibility to use the rotary kiln for torrefaction and carbonization?
Okay, so we have a rotary kiln for torrefaction, and we have at this point in time a pilot plant with a batch process for carbonization. In theory, you can use a rotary kiln for carbonization as well. However, due to the difference in temperature, torrefaction around 300, carbonization around 450 plus degrees, it is a different animal in terms of the rotary kiln. So you would have to have different materials to do that.
Okay. And so I guess it's an internal used for the torrefied pellets. But do you know a production price of the pellets of the torrefied biomass?
That is the big ingredient for the price of the torrefied product, and also then for the carbonized product, is the feedstock. What's the price of the feedstock? Roughly speaking, on torrefaction, you have a round number somewhere between 2.5 to 3 tons of raw material feedstock that go into 1 ton of final product, and hence that is a big driver of the cost of the end product. And for carbonization, even more so, because the ratios deteriorate. And as Hans-Jörg pointed out, then you need additional revenue streams in terms of heat or electricity in many cases to make the business case jive.
And I don't want to hold you up too long, but just a last question for myself would be, so do you plan to design a rotary kiln carbonization plant, or do you have plans for that?
Um, we are interested in doing that, if not necessarily ourselves, but maybe working with partners on that, because we see and we see the trend to bring the costs down. And I think for that, similar the experience, my experience, is similar to Hans-Jörg. I was in the PV industry, and when you look at the economies of scale that was achieved there, that is really, really impressive. A batch process is not so good in reaching economies of scale than a continuous production process. So we are interested in also expanding rotary kiln into carbonization.
So if anyone is listening who wants to do that, get in touch. If you want to see the Polytechnic's pilot plant in Germany, we had a presentation, I think a year ago or so, from the green carbon plant, which is also a quite interesting design actually. Um, and yeah, thank you very much, Harald, and also Hans-Jörg again. If anyone wants to see the presentations again, they will be online. So you don't get the actual presentation, but the recording. And